In the final lecture of the course, we will deal with radioecology and space radiation protection. So let's start with the definition of radioecology. What is radioecology, which is a relatively new term, because actually was really introduced only after the Chernobyl accident in 1986. So generally speaking, is a branch of ecology which studies radioactive substances interact with nature, how radioactive molecules interact with nature, how different mechanisms affect the migration and uptake in food chain and ecosystems. Investigation in radioecology might include aspects of field sampling, design field and laboratory experiments, and the development of predictive simulation models. It's a very interdisciplinary field, physics, chemistry, mathematics, biology, and ecology. And of course, radiation protection is a little bit the trade union. Radioecology formed the basis for estimating dose and assessing consequences of radiation pollution from human health and environment. Really became, as I said, an independent scientific branch in the Chernobyl accident. But let's say in the pre-Chernobyl data, there were already a lot of studies on the effects of radiation on plants and animals. And there were a lot of early data coming from laboratory exposure, accidents, especially in the Russian areas dedicated to the production of nuclear weapons. The areas of naturally high background that we discussed also in previous lectures, the nuclear weapons fallout that we saw in the previous lecture, and large-scale field irradiators like this one that were a lot used for crop breeding, for producing varieties of crops with special properties. This is actually, you see, it's not an unusual story. A few years ago in the 50s, it was easy to find these super seeds or these poppies that were created by atomic energy. But they are here to stay, as you see here, because more than 2,500 mutant crop varieties have been officially registered with the United Nations and the IAEA, and about 3/4 of the varieties were directly induced by gamma radiation. So you see there are many. This includes some very common that we eat every day, like granum durum, which is used in many pasta. Granum durum is so called because it's a wheat, but it's hard, so it's not flexible, and then it's easier to harvest, and it's a mutant of the normal wheat. But then, as I said, the story of radioecology starts with the Chernobyl disaster. That's how the nuclear power plant looked after the accident, and that's how a nuclear power plant works in general. You see, in a boiling water reactor, just like Fukushima or in Chernobyl, the simple idea is to boil water by the heat produced by nuclear fission. So you can essentially it's a turbine, but you boil the water with the heat of nuclear and not with the heat that comes from coal, for example, if you have a coal plant. The steam drives the turbines that generate electricity. In the event of a failure of the cooling system, you see, this is the steam line. But if you have a failure in the cooling system of the system, the water can boil off with the potential for the temperature to rise sufficiently for the core and the fuel itself to melt partially or completely. In most reactors, the effects of such meltdowns are minimized by surrounding the vessel in an airtight, steel-reinforced concrete containment structure designed to contain the fuel and fission products indefinitely. However, what happened in Chernobyl was that exactly in a stress test of the system that was put to the maximum power, reducing the cooling, it's a crazy test. There was a catastrophic explosion and the release of many isotopes in the environment. It's important to see that when you have this kind of nuclear accident, some isotopes are really short-lived, you know, like neptunium, molybdenum, that are tellurium. You see very high activity. We're talking about also xenon, which is 5 days, but it's a noble gas. We are talking about some 6,500 petabecquerel. So it's a huge amount of activity. Iodine was also huge, and we will see how important it was. Then you have a second phase where essentially you start to, you get rid of the fast, short half-life radionuclides, and you still have the mid half-life radionuclides. And finally, the final phase where essentially you are mostly dominated by cesium, cesium-137. Cesium-137 is 30 years in half-life, so it resists very long, and the activity is relatively high, and is easily distributed in the environment because it's easy to go into the tissue. Plutonium, of course, is much longer, but is extremely limited, the amount which is released in the environment. So on April 26, 1986, shortly after the exposure, you see that the dose rates, the exposure rates were indicated here. You see it's something, you have something like 20 gray per day in this red zone, and then you have 2 gray per day here. This is a scale of 1 kilometer. So within 1 kilometer from the reactor, you have the 20 gray per day zone. Then 2 gray per day, 0.2 gray per day. And in the town of Pripyat, 0.02 gray per day. This is the closest town to the reactor. So the doses, here we can see the doses absorbed by the you see by the emergency worker and by the population. You see that for the emergency worker, the dose are relatively high. You see there is a number of patients that receive doses between 6.5 and 16 gray, and essentially all of them died. These are real heroes in a way, because they try to extinguish the fire to avoid the even worse disaster, the complete meltdown of the core, even though they knew that the dose rate was so high that they were not going to survive. So these liquidators are really heroes, but then you see also others received fairly high dose, and other casualties were observed here, about maybe 30 casualties in total in the liquidators. For the population, the situation instead is dominated by low dose rate. Of course, you see that the accident involved, at that time there was the Soviet Union, but now we will say involved Belarus, Russia, and Ukraine, different cities. And you see that the cumulated dose, considering the population and the thyroid doses are not inclusive. This is mostly cesium dose. You see, in some areas, we're talking about some 40 millisieverts, 72 millisieverts, that are, as you have seen before, significant doses, but below 100 millisieverts. So in a region where from Hiroshima and Nagasaki, considering that the exposure was low dose rate, you will not expect a significant increase of cancers, with the possible exception of a small increase of leukemias. As a matter of fact, that's exactly what was observed. You see that these are the cases of leukemia that are childhood leukemia that are practically insignificant. This is the Chernobyl case. But instead, if you look at the thyroid cancer, here you have a very sharp increase. However, make no mistake, because you see here also the baseline cases for female and male. And these baseline cases generally increase. So not all of this increase is due to the radiation. A large fraction of this increase is due to the screening effect. So of course, the fact that people were starting to look much more in detail into thyroid cancer. The last report is from 2018, and it has been estimated that there were almost 20,000 cases of thyroid cancer in that period. And approximately 50%, with fairly large uncertainty, as you can understand, can be attributable to radiation exposure. Fortunately, thyroid cancer is generally non-lethal, so the number of casualties associated to this cancer is low, is very low, but still, you know, because affect mostly the children is a big tragedy. And we will see later why this was the reason of this enormous success of thyroid cancer. In Chernobyl, it was defined, as I told you before, that there can be 3 phases in the contamination of the environment. The first phase is the, let's say, is the from 0.1 to 1 month after exposure, then the first year, and then beyond the first year from exposure. So in the first 20 to 30 days, there are severe effects to the biota because the gamma exposure, those rates were higher than 20 gray per day, as we have seen. And the exposure you can see here, this is the time after the accident, and this is the contribution in absorbed dose rate in air, is really dominated by short-lived isotopes like molybdenum, tellurium, xenon, iodine, and barium. There were then high doses to thyroids from iodine. This is a shame, of course, and this goes to the fact that the accident was kept secret by the Soviet Union at that time. So the population was not informed. As a result, you have a large release of iodine in the environment that then falls down in the fields. The cows eat the grass. We will see that the cows in the Chernobyl area, in the Ukraine area, were particularly poor in iodine, so they absorb a lot of iodine. This iodine ends up in the milk, and if you drink fresh milk, this contaminated iodine will end up in the children and will accumulate in the thyroid, releasing relatively high dose, actually very high doses of radiation to the thyroid. All these could have been easily prevented simply by informing the population not to consume fresh milk or vegetables fresh vegetables. And of course, also, which is a standard now, also distributing stable iodine. Stable iodine, of course, if you take excess of stable iodine, you saturate your thyroid, and so you will not be able to accumulate radioactive iodine in the thyroid. Unfortunately, this was not done, and this is criminal behavior that led to this tragedy of 10,000 childhood thyroid cancers. So in the first phase, within the 10-kilometer zone, the red zone, you see the effects were quite disastrous. You see all these plants that actually died. There is a mortality to most sensitive plants and animals, and the reproductive impacts of many species of biota. It's interesting, you see here, this is the cumulated dose, let's say, that was accumulated by the organism. And these are the radiosensitivity you see for minor effects and intermediate to severe effects of different components of the environment, you know, from the forest, rodents, soil invertebrates, and so on. So the most sensitive region here, like moss lichens, grasslands, tropical rainforest, old fields, shrub, these were definitely affected and seriously impacted. In the second phase, now we're talking about the phase from 1 month to 1 year. Now the short-lived isotopes have decayed. Now the contribution to those rates changed completely, you see. And also from the radioecology point of view, we are the phase of radionuclide migration. So for example, here you see these trees where the radionuclides were deposited here, this area of the tree is completely burned, but this area of the tree is still alive. So after the first phase, the radionuclides now go into the soil, and the plants starts to find strategies to survive, those that could survive. Those rates are chronic, are in the third phase. Instead, we go into chronic those rates, less than 1% of the initial. Beta and gamma contributions are comparable depending on cesium and how much cesium. Cesium and strontium essentially dominate the dose. Indirect effects dominate, and genetic effects persisted. There have been examples of, for example, in barn swallows from Chernobyl, they had a higher frequency of abnormal sperm than did control. Concerning the plants, there is quite a number of effects that started to be observed in terms of mutations, non-lethal mutations. Leaf gigantism, the plants are much more tolerant to mutations than mammals. Hardwoods that we are seeing were more radioresistant. They were able to resist even extremely high doses. Only part of the hardwood was killed. And there was a shift in the ecosystem. So pine stands that were more sensitive were replaced by grasses and hardwoods that there was a slow invasion of hardwoods in the environment. And the genetic effects are also extended, as I said, again, in Arabidopsis, which is a standard plan, 4 to 8 times more mutations than in controls. So concerning the general effects to plants, you see we are now here in a region where you have relatively small effects, but you see mutation, twisted needles, for example, inhibition of photosynthesis and transpiration, chromosomal aberrations in meristem cells, and short-term sterility. Now, concerning the animals, there was a chronic radiation syndrome, so reduced body mass and fat reserves, increased mass of lymph nodes, liver and spleen, thickening of lower gastrointestinal lining, mortality of cattle, that, by the way, as I told you, were receiving particularly high doses from iodine because they were actually eating the grass. And the transfer of radioiodine to thyroids was 2 to 3 times greater than normal due to the endemic deficiency of stable iodine in local soils. 70% of the cattle still had depressed thyroid function, 70% depressed thyroid function at 50 gray, and you have an 82% reduction at 280 gray. So concerning rodents, you see rodents population was timefold reduced with dose rates between 1 and 30 gray per day. At about 0.1 gray per day, there was temporary infertility and reduced testis mass, chromosomal aberrations, but the number of mice recovered within 3 years by immigration. For soil invertebrates that are also very important, of course, 60 to 90% of the initial contamination was captured by plant canopies, but the majority washed off to soil and litter within several weeks. So in the second phase, from the canopies, you go to the soil. So now you touch the invertebrates whose population was reduced some 30-fold. The dose and effects to invertebrates in forest litter were 3 to 10 times fold higher than those in agricultural soil. And the 30 gray altered community structure, species diversity for 2.5 years. Finally, there is a number of indirect effects. One is the story of the red forest, for example, the so-called Wormwood forest, which is a 10 square kilometer area surrounding the power plant within the exclusion zone. And it's also called red forest because of the ginger brown color of the pine trees after they died following the absorption of high radiation. Now, what happens is that you have a huge rate of decomposition of the plants in this region. And also because you don't have soil invertebrates, they are also affected. So the plants are not decomposed. properly, let's say. So you produce a huge mass, you have a liter mass loss is 40% lower in the contaminated sites relative to sites with a normal background radiation level for Ukraine. And this results in building that brush over decades, which potential kindling for a catastrophic forest fire in the future. So you see that a shift in the ecosystems very often gives disasters, unexpected, let's say, when nobody would think that this could be a problem, but now the risk of fire is now enormous in this forest compared to normal forests. Now, there is also the problem of human abandonment. So the Ukraine decided to give large evacuation. This is the city of Pripyat that was completely evacuated. So it's 135,000 people and 35,000 cattle were evacuated. Dozens of towns and villages were deserted. This was a tragedy by itself. This huge evacuation without a real plan for resettling caused poverty and eventually death of many, many more people that would have been necessary. In fact, this evacuation was limited to a very minimum in Fukushima, and the people were then quickly returned to their houses. As a consequence, though, interestingly, if you look at this is now the contamination density in kilobecquerel per square meters, and this is the counts of elk and wolves. You see that there are many elks and wolves in the contaminated area, and if you look at the relative abundance in number of animals per square kilometers, you see that in 1986 there was nothing, essentially. No elks, no deers, no boars. But you see the very sharp increase after 1986. So is this due to low-dose radiation beneficial effects? The answer is no. This is a well-known effect of the evacuation of humans. So when the humans go away, the animals come in, and even in the aftermath of the worst nuclear accidents, nature flourishes now. So what is the long-term impact of this low-dose rate exposure that still is ongoing to the animals remains to be seen. At the moment, let's say the red zone in Chernobyl is a sort of open-air lab to study radioecology, because you have a high dose rate and you have all kinds of animals, plants, and natural life happily flourishing without demand. The second, of course, is Fukushima, that you probably instead remember. Of course, Chernobyl you cannot remember, but Fukushima maybe you remember, because this happened on March 11, 2011, was a 9.0 magnitude earthquake, a terrible earthquake with the epicenter in the Japan Sea. And this caused a tremendous tsunami, and it was the tsunami that actually damaged with a wave of 14 meters, maximum 39 meters at Taro Town, that caused the damage of the Fukushima. Actually, the earthquake and tsunami itself was a tremendous tragedy, you know, with 14,000 people died and 10,000 people were missing in 18 prefectures. But in addition to this, there was the accident in the Fukushima Daiichi nuclear power plants. Even though all operating units were shut down safely when the earthquake occurred, the tsunami, you see, the tsunami, which was higher than predicted, let's say, was higher than the safety prediction that was done, caused the loss of power, and eventually all motor pumps become inoperable, and with the consequence, of course, of not being more able to cool down the reactor, and eventually this led to the explosion in Unit 3 and Unit 4. The interesting, you see the reactors exploded between 12 and 15 March, but radioactive probably was leaking already before the blast. What is interesting is the wind. There was a lucky situation, if you want, because you see the wind was going in the east direction. So originally, all the radioactivity, you see here the radioactivity map, was going toward the Pacific Ocean. It was unfortunate only on March 15, there was a change of wind that brought radioisotopes back toward Tokyo. And then the rain, the precipitation along Japan's central mountain ridge created a line of contamination, which is clearly seen by aerial surveys. The other problem, which is unique in Fukushima, is the large release, of course, of radioactive material in the water, with intentional discharge of radioactive water and leakage of highly radioactive water. So this creates a large contamination around the coast, whose meaning still remains to be studied. It's also new, is not known. So if you compare Chernobyl and Fukushima, the total release of radioisotopes was less than 10% in Fukushima than in Chernobyl, because Fukushima was a much more modern structure with much more protection. It is possible, though, that there was a higher initial release of xenon-133 in Fukushima for the nature of the explosion, but 133 xenon has a relatively short lifetime. Information and prevention were, of course, much better in Japan than in Soviet Union. The concrete vessels in Fukushima prevented release of significant amounts of strontium, americium, and plutonium. The marine contamination, as I said, is a completely new issue in Fukushima. And that's again a comparison for the fallout. You see, that's the amount release of iodine 131 and cesium 137. You see that definitely was much higher in Chernobyl than in Fukushima. And you see the fallout comparison here of cesium around Fukushima. You see the red zone here, and around Chernobyl it was, of course, much larger, and with much larger area contaminated. So concerning the liquidators in Fukushima were much more controlled, of course, than the liquidators in Chernobyl. Actually, it was set the limit to 100 millisievert exposure. So you see that the most of the liquidators are below 100 millisievert. There were, though, a few exceptions. Okay, 100, 150 that was measured before. There were only a few people, maybe a couple of dozen of the liquidators with significantly higher doses. And so the average dose, you see, was 24 millisievert for the employees of TEPCO, which is the company that was handling the Fukushima Daiichi nuclear power plant, lower for the contractors that, of course, were not so exposed. So in total, about 11 millisievert, but with maximum doses, you see, quite significant in the order of 700 millisievert. So, of course, this population is a population which is a large population, about 20,000 people at the end, which is now strictly under control because there's 20,000 people exposed to a relatively high dose. So the Japanese, of course, are following a program now in Fukushima, which is similar to the RERF in Hiroshima and Nagasaki for the follow-up of the survivors, both liquidators and population. So in summary, for the radioecology, we have 3 periods, the period 1, the period 2, and the period 3. One of the main problem is especially when you go into period 3, we know that there are noticeable positive impacts on nature, but we don't know the long-term genetic consequences, and this will be studied both in Chernobyl and in Hiroshima, in Fukushima. I'm sorry, Fukushima. It is still unclear, in fact, what is the extent of inherited transgenerational effects from chronic low-level irradiation, what is the significance of molecular effects that has been observed, but we don't know how significant they are for individuals and population, and what are the consequences of the marine environment contamination in Fukushima. The second part of this lecture will be instead focusing on the extraterrestrial environment. So now we move from the Earth to the space. Why we do that? We do that because actually now the life in space is becoming more and more a reality. For many years we had the International Space Station in orbit, but now the plans go toward exploration. And the first one will be the Deep Space Gateway. This is a slide from NASA showing the plans for the Deep Space Gateway that you see. The Orion spacecraft, we have seen it already in 2020. This was from SpaceX, from Elon Musk. And then eventually we will go to a gateway in lunar orbit by 2026, with the idea of having eventually a moon base for permanently living on the moon with exchange of crew. And of course, the moon is only one step in the plans for exploration, because you can actually go, of course, you can go to the moon, but you can go to many other places. You can go to asteroids, you can go to Mars, which is definitely appealing target, even to outer planets like Saturn and so on. The problem is that when you shift from the Earth toward the external side of the solar planet, the dose rate increase. The dose rate increase because the universe is permeated by galactic cosmic radiation that comes from the supernova, emitted by the supernova. They are very high energy particles. All kinds of particles, from protons to uranium, can be formed. The magnetic field of the sun protects the solar system. So if you are closer to the sun, the dose rate is lower than if you are far away from the sun. And moreover, the sun has phases of solar maximum and solar minimum that have approximately an 11-year period. And in solar maximum, the magnetic field is stronger, and in solar minimum, the magnetic field is weaker. So in solar maximum, the dose rate is reduced of approximately 1/2 as compared to the solar minimum. And the doses, as you see here, are quite significant. We are talking about some 1 millisievert per day in low Earth orbit, up to 3 millisievert per day if you go in the outer solar system. We will see a little bit more. Why? So what are the risks of human exploration? Of course, you have technology, you have space debris, you have this kind of engineering risk. But if you go to human factors, let's say to health risks, then the dragons are space radiation, human factors, and microgravity. Now, microgravity, you see, we know that in the weightlessness, there is a number of physiological changes, including cardiac arrhythmia, osteoporosis, muscle loss, and so on. But we know the risks very well, and we also know the countermeasures, like physical exercises. Human factors are especially related part to acute medical problems, but especially to psychology, but this also is, the risk is known and the countermeasures are known. For space radiation, the problem is more complicated because the risk, as we will see, is not known very well, and the countermeasures are not easy to find. So the radiation field that we experience is divided into 3 parts. One is the solar particle events. These are generally associated with coronal ejections from the sun. They are medium to high energy protons. During solar activity, the solar particle events are more likely and more intense. So in a way you would like to avoid the solar maximum if you want to avoid the solar particle events. But on the other hand, as we will see, the galactic cosmic radiation is lower. In principle, they are even lethal. We will see this in a second, but they are easy to shield. The other component that was the main component on the International Space Station when you are in low Earth orbit, so when you are in an orbit, a space station is at 250 kilometer altitude to Earth. In this case, it's the protons trapped in the magnetic field of the Earth that give the main dose contribution. And finally, instead, everywhere isotropically in space is the galactic cosmic radiation, as I said, that is composed by protons and high energy and charge HZE particles, heavy ions, let's say. And in this case, the problem is that really we don't know exactly the biological effects. And of course, the shielding is a big problem, as we will see. So this is an example of coronal ejections. You see, this is the SPE that was occurred in February 2011. You see, it's very spectacular on the sun. You have the emission of a lot of protons. The fluence of the protons is here. Just to give you an idea, this red line gives the fluence of galactic protons per year. So you see how much higher is the flux coming from protons. However, you see, these are all major events measured in many different years. Most of them are soft. So this is low energy. So you see only the spacecraft shield cuts away all these protons away. And still, if you have a little bit, this is the external, the 5 grams per square centimeter aluminum shell. Then if you add the internal shielding due to the racks, you get rid of quite a large component also of this one. So shielding is very easy for solar particle events, and the real risk is mostly if you are in EVA. If you are in EVA, for example, on the moon surface, and you are very far from the base, because the warning signals and the forecast signals are not so clear, there is a risk that you can be exposed to a lethal solar particle events and you cannot shield yourself. The galactic cosmic radiation is a different problem because it's a constant low dose rate, so there's no risk of acute effects. But you see, it's a peculiar spectrum. The black point here gives you the spectrum influence of the galactic cosmic radiation. You see, it's mostly protons. Then you have some almost 10% of the helium. And then the others, the other ions are all in the order of 0.1%. So a lot of protons and very little heavy ions. You see, this is the CNO group, carbon, nitrogen, oxygen. And this peak down here is the iron, which is preferentially produced, is the heavy ion preferentially produced in the stars. However, we don't really care about the fluence. We care about the dose, that is the white points that you see here. And of course, the dose is proportional to the square of the charge. So this point down here go up. And if you multiply them by the RBE, by the biological effectiveness, they go up again to the point that, you see, the iron alone gives a higher biological dose, let's say equivalent dose, than protons. So heavy ions are very important here, high LT heavy ions. And you see, the spectrum is also a problem because this is the spectrum for protons, helium, carbon, and iron. Of course, different magnitude, many more protons than iron, but the shape is always the same. And you see that the shape is peaking around 1 GeV per nucleon, very energetic, with tails that go to much, much higher energies. It's a log scale though, which shows you how difficult it is to shield this particle. They're very energetic. So unlike trapped protons or solar particle events, protons, shielding of these particles is very, very difficult. Actually, there has been a careful measurement of the dose going to Mars. So outside of the magnetic field, this has been carefully measured with the RAD instrument on the MSL, the Mars Space Lab of NASA, that was launched in November 2011, landed on Mars in August 2012, and then there was the rover, the Curiosity rover, which is still on Mars. So with this instrument, it was possible to measure carefully the dose, and this summarized here. You see for the cruise, the dose was 0.46 milligram per day or 0.21 milligram per day. If you apply the correction factor for the RDE, this goes to some 1.84 millisievert per day or 0.64 millisievert per day. Of course, on Mars, the dose is much lower. It should be at least 1/2, because you are protected by the solid shield of the planet itself. No, you are protected from compared to the space where you are irradiated for pi. On Mars, you are protected by the shield. This is even less than 1/2, because Mars also has a thin atmosphere. And you see that if you calculate the dose for a Mars mission, you approach 1 sievert. Easily, you approach 1 sievert. So this is a very significant dose, as you know now. And these are the doses also for the 1-year mission on the space station, which is also quite significant. You see, if you take the solid cancer is the dose to the colon, and the leukemia is the dose to the bone marrow. And you see that depending if you are in solar minimum or in solar maximum, you see, but if you are in solar minimum, for example, the solid cancer dose is about 0.1187. So it's kind of significant dose even for the 1-year mission that has been done. In fact, has been done. You see, these are the famous Scott twins. One of them was in space, the other one was on Earth. And it's quite a number of this is published. The results from this twin study was published on Science, in the journal Science, in April 2019. Quite a lot of effects were observed, and there was a general agreement that the radiation effects were probably the one with the worst prognosis, and eventually with the most concern for being more serious when you move from the low Earth orbit to deep space. However, do we have an increased mortality in the astronauts cohort? The answer is generally no. You see, this is the mortality for US males, survival probability as a function of the age. So this curve here gives you the survival of US males, and you see that, of course, this starts at 30 with very close to 1. And then when you go to 75 years, you are approximately at 50%. And then, of course, if you go to 100 years, you go to 0, because sooner or later we have to die. This is now the yellow dots are the astronauts. So this is interesting. You see, in the young age, let's say between 30 and 55 years, you have increased probability of death, reduced survival. But in the late age here, you have an increased survival. Why is that? Well, this is essentially dominated by the occupational risks. As you know, many astronauts died. So if you take, there were 2 tragic accidents of the space shuttle and other accidents previously. So the occupational risk is very high, 7.5% so far. Hopefully will be reduced in the future. So this is essentially occupational risk, and this is the so-called healthy worker effect. So astronauts are very healthy individuals. They are selected because they are healthy and they are in good physical shape. So it's not surprising that if they survive the occupational risk, eventually they come out with a higher survival than the average US males. However, the risk, you see, the risk of cancer death, the problem you see in this estimate, this is an estimate of the percent risk of cancer death for different radiation exposure, including lunar colony and Mars mission. And you see that the problem is not so much the point estimate here that you can do if you calculate, of course, always using Hiroshima and Nagasaki eventually. You see that for a Mars mission, the best estimate that you can do is in the order of 4%, which is coherent with the idea you can already imagine that is coherent with the idea that you take 1 sievert. But the problem is that the uncertainty on this risk is very high, so high that the risk can actually jump between 1% and 30%. And you will realize that if it is 1%, you will not bother very much, considering that your average, your normal background is 30%. But if it is 25%, then you almost double the risk of cancer. So reducing the uncertainty is mandatory. How to reduce the uncertainty? Where is the uncertainty coming from? It's coming from, you see, this is the fold uncertainty. It's coming from many different sources. But the most important is radiation quality. So the fact that we are now dealing with a mixed field with the high LET heavy ions and not with the conventional radiation that we know from Hiroshima and Nagasaki, gamma rays, give the higher radiation quality, the higher uncertainty factor. Then, of course, dose rate effect. We have already seen that it is very uncertain how to extrapolate from the acute situation in Hiroshima to the chronic situation in space, or in general, also on Earth exposure is uncertainty almost at a factor of 2. The transfer of risk across populations, which is typical also for Earth, you have to extrapolate from Japan to non-Japanese. Space dosimetry gives some contribution. Errors in human data, so the uncertainties that we have, give also a significant contribution. And finally, the interaction with microgravity and other space stressors gives a further contribution to the uncertainty. Moreover, we know of at least one radiation-induced effects in astronauts, and this is cataracts. We know this because there have been a comparison, epidemiological comparison, let's say, of the low exposure groups. This is a group of astronauts that essentially never flew or only flew for taxi missions, and high exposure group. But high exposure group was characterized by whole body dose of only 8 millisievert or more. And you see that the survival without cataracts, both for all cataracts and non-trace cataracts, that are the type of cataracts that is considered to be more likely to be radiation-induced, there is a significant, let's say, not really increase in the risk, because you see, if you live long enough, eventually the two groups go to the same value. But this is because cataracts is like cancer, it's an aging disease. So if we live long enough, we all get cataracts. But the onset of cataracts is shifted to the right for astronauts, showing that you get cataract when you are younger. And that's definitely something that you don't want. So this is now the only radiation-induced effect observed in crew members, and also shows you how the latency time is important in these risk estimates. So also for cancer is the same. It's not really a matter of what is the probability of cancer. It's a matter of how soon you will get the cancer. So finally, countermeasures. Can we reduce this risk? Can we get rid of this risk, which is now considered the main health risk for a mission to Mars? Well, you see, this is a typical statement that I took from one book of radiation protection. It's everywhere. You know, in radiation protection, we know that there are 3 means to reduce exposure. You can reduce the exposure time, increase the distance, or shielding. But in space, you don't want to reduce the exposure time. Actually, you want to increase the exposure time because you want to stay more time in space. You cannot increase the distance because the source is isotropic, so the radiation is coming from everywhere. It's coming from the far supernova, so there's no point in increasing the distance. So the only thing you can do is shielding. The problem of the shielding in space, though, that unlike on Earth, where of course you want to use material with high density, because then the absorption coefficient of photons is higher, So typically you use lead on Earth. In space, the physics is different. We have seen this in the physics. You know, the ionization goes as Z divided by A of the target. And the fragmentation as A to minus 1/3, the Bragg-Peters formula. So the attenuation of the beam decrease when you increase the mass. So you want to use light materials. That's essentially because, you know, the usual problem that in physics, when you increase the mass of your target, you increase the cross-section, but you increase the volume more than the surface, because the volume goes with the third power and the surface with the second power. Now, in space, the only thing that really matters is the shielding effectiveness per unit mass, because you have to control the mass. You cannot have an indefinite mass, except on the, if you use in situ resources in the bases, then you can say, okay, I go in the caves. For example, on Mars, you can imagine you go into the caves, in deep caves, and then you have a huge mass of shielding. But on the spacecraft, this is impossible. So the best material, if you want, is the liquid hydrogen. But this is, of course, not very easy to use, of liquid methane. Polyethylene is good, water is good, aluminum is pretty bad, lead is probably the worst. And this is the region here where there is more potential for new materials, you know, polymer composite, hydrides, lithium hydrides are very much studied. That's where you can develop new materials that are multifunctional, so they can work as a, for example, for shielding of the micrometeorites, but also for shielding of the of radiation, and can be used to reduce the risk. This is an example, though. You have to keep in mind, you see that if you, these are calculations of done with the code of NASA HDA-Tron of the average bone-forming organ, bone marrow dose equivalent as a function of the thickness of the shield. For in free space, in lunar surface and Martian surface, the dotted line are in solar maximum, the solid line are in solar minimum, so of course they're much higher. And you see that aluminum is here in the blue, and the one down here is liquid hydrogen. So if you take liquid hydrogen, you can go up to a 90% reduction in those. So that would be really, let's say, a solution, because you will reduce, for a mission to Mars, you will go from 1 sievert to less than 0.1 sievert, but that's not easy. Polyethylene, you get the best 50%, and aluminum only 30%. So it's really necessary to find some better solution, let's say. One nice way to test this shielding material is to do it at accelerators. We do it a lot at GSI, and you see it here. It's a comparison of the Bragg curves for polyethylene, Kevlar, Nextel, aluminum. Kevlar and Nextel are two typical multifunctional materials. They're used for shielding of micrometeorites. And you can see from the slope here and the position of the peak that aluminum is bad and polyethylene is good. And Kevlar and Nextel are somewhere intermediate here in the ability to reduce the shielding. This linear part of the Bragg curve is actually, you see, this is a study previously done by the Lawrence Berkeley lab and the Brookhaven National Lab. They found out that the percent dose reduction for low thicknesses of shielding material, this is polyethylene, is essentially almost linear. So you can use this slope to give an estimate of how good are the shielding, you see it. And you see that copper and aluminum are very bad. And epoxy is air, essentially, you know, it's the foam is very good, actually. You see also graphite is good, this is carbon, and so on. So you can actually test the goodness of the shielding on Earth using accelerators. And finally, if you are not happy with not so much hopeful with the passive shielding, you can still imagine to copy the Earth and to do the shielding with the magnetic shielding. The problem is that for SPE, you could do something like that for SPE if they are directional, but the SPE, as I told you, are easy to shield. The problem is how to do it for GCR. To do it for GCR, you need a system, very complex system like this one. You see, this is now a model for a spacecraft to going to Mars that was designed by Samuel Ting, who is a Nobel Prize at MIT in US. The idea here, this is the area of propulsion, energy, and life support, and this is a huge magnetic field, and is a toroidal magnetic field, and the internal part of the toroid is zero, of course, if you remember how a toroid is done. But you see the BL here is 14 Tesla meter, so this is a very, very high 70,000 Gauss of magnetic field if you want to have a significant shielding of the GCR. And to do this, you need high temperature superconductive magnets that to run them in space remains to be demonstrated. So this concludes this lecture and the whole course. I thank you very much. And of course, I hope to see you at the next Q&A, and I hope you enjoy the course.